Okay, so we're going to talk about a density curve, and in particular, we're going to talk about a normal distribution. So we've talked about z-scores and how the z-score finds how many standard deviations above or below the mean is. And we talked about how z-scores don't have any units of measurement. So now we're going to talk about a bigger picture, which is the normal distribution. Sometimes the overall pattern of a large number of observations is so regular that we can describe it by a smooth curve. So this is a density curve. It's a histogram. You can tell it's a histogram because the bars are touching. It's a histogram of the scores of 947 seventh graders in Gary, Indiana, on the vocabulary part of the Iowa Test of Basic Skills. Scores on this test have a very regular distribution. The smooth curve drawn through the tops of the histogram bars is a good description of the overall pattern of the data. So if you guys look at the histogram, you can see that it is very symmetrical. It is unimodal. It's not right skewed or left skewed. It's very well behaved. There's the bulk is in the middle. It's got about the same number of small low bars on either side. And so what we're going to use is this smooth curve. That's this. Just to kind of give the general idea of the shape of this histogram. All right, so let's talk about a density curve in general, and then we're going to turn our attention to a normal curve, which is a specific kind of density curve. Okay, a density curve is a curve that is always on or above the horizontal axis. Think about what that means. And it has an area of exactly 1 underneath it. So if you think about area of exactly a 1, think about area as a percent. If it has an area of 1, then 100% of my data is going to be under that curve. A density curve describes the overall pattern of a distribution. The area under the curve within a particular interval is the proportion of all observations that fall in that interval. All right, that last part, that's a good piece. Let's read that a little slower and let me show you what that means. The area under the curve within an interval. Okay, so let's say I have a curve. Let's say these are your stats grades. And let's say we average at an 80. There's a 90. There's the 100. 70, 60. Okay, so our grades are ranging from about a 60 to 100. Looks like the mean and the median sits at about an 80. Okay, now what this is saying is that the area under this curve, so all of this shaded in part, represents 100% of the stats grades. Okay, so that's what that means. Okay, now I'm right here. It says the area under the curve within an interval. Okay, so now instead of looking at all the grades, I'm going to cut it off and give you a specific interval. So let's say I want to go from a 75 to a 90. I want to know the percent of students who have an average between a 75 and a 90. So the area under the curve within this interval, okay, so now we're just talking about this area, is the proportion of all observations that fall in that interval. So if I knew how many pieces of data were in here between a 75, and a 90, and did it out of the total number of kids, that would give me the percent of area that's represented by that interval, by that shaded part. And we're going to work with all that today. Let's see. It is a good description of the overall pattern of a distribution. Outliers are not described by the curve. A curve does not address outliers at all. No set of real data is exactly described by a density curve, but it's a really, really good estimation. The curve is an approximation that is easy to use and accurate enough for practical use. So I hope if there's one thing you've kind of taken away from stats thus far, is that stats is not an exact science. We are predicting. We are making conjectures. We're gathering data and kind of telling you the gist of what we see. But the conclusions about statistics are not, it's not an exact science. So the curve is an approximation that's very easy to use and widely used, and it's very accurate enough to use for practical use. Okay. The median of a density curve is the equal areas point. A point with half the area of the curve to the left and the other half to the right. And that makes sense for median, because median, when we talked about individual pieces of data, was the middle number. Since a density curve are idealized patterns, a symmetric density curve is exactly symmetric. In real life, it never is, but in theory, it is perfectly symmetrical. The median, therefore, is the center. So if you look at this first graph, this is a beautiful graph, very symmetrical. So my median is right here in the middle. And guys, because I'm symmetric, and you already know this, the median and the mean are going to be equal here. Let's see. If it's not symmetric, find the balancing point. Okay, so now we have one that is right skewed. If I had to balance it, again, like if this was a tray of food or dishes or Legos, and I wanted to balance it so that it wouldn't fall, I would balance it about there. But you know that because it's right-tailed, the mean is going to be a little bit greater than the median. The mean, as we know, is the median if the curve is symmetric. If the curve is skewed, the mean is pulled in the direction of the skewedness. And again, we've already talked about that. You already know that. Okay. The notation for the mean of a density curve is mu. Okay, so now we've talked about this. Mu and sigma are for population data. This is mean, and this is standard deviation. If you don't already know that, you need to make a note card and put this on the note card. And it needs to be somewhere where you can always see it when you're doing your stats. X bar and S sub x are the mean and the standard deviation when we have a sample. So mu and sigma for population, X bar and S sub x for sample. Okay, so again, the notation for the mean of a density curve is mu. The notation for the standard deviation of a density curve is sigma. X bar and S sub x are computed from the actual observations. That is your sample. Okay, so let's check our understanding. It says explain why this is a legitimate density curve. Okay. Area equals 1. Says it right there. And graph is above x-axis. There you go. got to have a total area of 1. Everything's got to be above sea level. About what proportion of observations lie between a 7 and an 8? The total area is a 1. It's saying that this area between 7 and 8 is a 0.12. So you can say 0.12 or you could say 12%. Trace the density curve onto your paper. Mark the appropriate location of the mean and the median. Well, of the mean, and then number 4 wants the median. Okay, so I'm just going to do it right here. So the median, we are skewed left, so I'm going to pull the median a little off center. There's my median. And then we're left skewed, so that's going to definitely pull the mean down. So I know that my mean is less than my median. All because it's left skewed. Okay. Okay, this is big stuff. This is your normal distribution. We're going to talk about normal distributions from now until May, almost every single day. So here we go. A normal distribution, which is abbreviated capital N. And notice, every time you see the word normal, its N is capitalized, or it should be capitalized. That's because the normal distribution is its name. So just like you always capitalize the first letter of your name, or you should, we're going to capitalize the first letter of normal. So abbreviated N comma mu, or in parentheses mu comma sigma. So if I gave you this, this is a normal distribution with a mean of 75 and a standard deviation of 3. This is the mean and this is the standard deviation. And I know it's a normal curve. Now let's talk about normal curves. A normal curve describes a normal distribution. All normal curves are symmetric. So if you're strongly skewed, you're not normal. All normal curves are symmetric, single-peaked, and bell-shaped. Any specific normal curve is completely described by its mean, mu, and its standard deviation, sigma. Okay, so we have 2 normal distributions here, 2 normal curves. The mean is located in the center with the median. The reason why? Because we're symmetrical. The standard deviation controls the spread of a normal curve. Okay, so if I'm looking at these 2 curves at the top of your screen, the first one, the one on the left, has a higher standard deviation than the second one because the first one is more spread out and standard deviation measures the spread. So while they may have the same mean, so like let's pretend these were stats tests. Let's say the stats test average was an 85 for both classes. But this one could have a standard deviation of, I don't know, 10 points, and this one's going to have a standard deviation of 3 points. So the second one, the data is tighter. It's less spread out, so it has a smaller standard deviation. The first one, the test scores are much more spread out, so it has a higher standard deviation. So they have the same mean, but the curves are going to look totally different. And that's why a curve is defined by its mean, tells you where it's centered, and its standard deviation gives you insight into how spread out it is. Notice the more spread out it is, the less peaked it is. Remember, both of these curves have the same amount of area underneath them. They're both 100% of the area, like their area is 1. So if the first one has to go more spread out, then I have to bring the top down to keep the same amount of area. So the tighter, the less spread out it is, the taller the hump gets. The mean is located in the center with the median, and the standard deviation controls the spread of a normal curve. Okay, so let's really analyze this normal curve. So here she is in all her glory. Now, I've got my mu in the middle, dead center. Notice I'm not talking about the median, I'm talking about the mean. This is my mu. Okay, this curve never touches the x-axis. So when you draw it for me and when you draw it for your AP graders, I want it to look like that. I don't want to see this or this. It can't do this. Like, don't get cute with the ends of it, because you're saying, oh, there's a little bit of data here and then it really opens up and there's some data out here. That's not true. It approaches this like an asymptote, but it never touches it. Okay. Let's see, what else can we talk about? Let's talk about the standard deviations. So you can see that this is the highest point and this is concave down, but then this is concave up. It changes concavity at what's called transition points, which happens one standard deviation away from the mean. So when you are one standard deviation on either side of the mean, it changes from concave up and it starts turning concave down. Now notice this curve only goes 3 standard deviations in either way. Most of your data, and we're actually going to get very picky today about how much data we're talking about, but the majority of your data is going to be within 3 standard deviations of your mean. However, I did not say all. 100% of your data is not necessarily within 3 standard deviations of your mean. So that's why those lines, that curve does not touch the x-axis, because you have to leave room for those crazy pieces of data that are out there. Okay? Okay, back to the Iowa test. Suppose that the distribution of scores over time is exactly normal, again, capital N, with a mean of 6.84 and a standard deviation of 1.55. This curve shows the normal density curve for this distribution. Okay, so let's talk for just a second about these numbers down here at the bottom. Let's look at these. And let's see if we can figure out where they came from. So this is my mu. That's him. Now notice there are 3 tick marks to the right and 3 tick marks to the left. These 2 lines never touch. Neither do those 2. They get really close, but they never touch. You can see that there is area under the curve beyond 3 standard deviations. Again, it's not 3 standard deviations does not hold 100% of my data. It's almost 100%, but it's not quite. Okay, now my standard deviation is 1.55. So think about how they got the 8.39. They added 1.55 to my mean, and that's where this number came from. All right, to get the 9.94, they did 6.84 plus 2 times 1.55, because he's 2 standard deviations away from the mean. That's where he came from. Then they did 6.84 plus 3 times the standard deviation, and that's where that guy came from. And then to get these, I'm going to do the same thing. I'm just going to subtract because it's below. So this is 1 standard deviation below, 2 standard deviations below, 3 standard deviations below. Okay, now that we kind of have this distribution, how unusual is it for a Gary, Indiana 7th grader to get a 9.94? Okay, so let's look. 9.94, that puts this kid right here. And I want to know how unusual it is. Remember, the area under the curve represents all your pieces of data. So look where that kid is in relation to everybody else. So this is actually very unusual. That is ridiculously high. All these people got lower than him, and only those percentage of people got above him. Remember, area under the curve represents the proportion that holds that value. Okay, so now I want to be much more specific. Instead of just saying, hey, yeah, it's kind of unusual, I want to know exactly how unusual it is. Okay, here's the 68, 95, 99, 7 rule. Approximately 68% of the observations fall within sigma of the mean mu. Approximately 95% of the observations fall within 2 sigmas of the mean mu. All right, here's the good one. Approximately 99.7, not 100%, but really, really close, of the observations fall within 3 sigmas of the mean. Okay, so now look at that graph that I've got. Approximately 68% of the observations fall within sigma. So that means 1 sigma to the right and 1 sigma to the left. That holds 68% of my data. So this area right here is 68% of the total area. So guys, what we're saying is if a statistician collects data and his data is deemed normal, then he can conclude that 68% of whatever it is that he's measuring, those subjects, will fall, whatever he's recording, will fall within 1 standard deviation of the mean. So their z-score would be between a 1 and a -1, because remember, the z-score measures how far away from the mean something is. Okay, now check this one out. We go from 68 to 95, and that's within 2 standard deviations. So now I'm looking all the way over here, including this middle chunk, and all of this. So everything you see that's yellow is 95% of my data. So 95% of the observations that you take, whatever it is that you're recording, will fall within 2 standard deviations of your mean if your data is normal. And then the very last one, 99.7. So 99.7% of my data lives within 3 standard deviations of the mean. It is not 100%. It is not all-inclusive. There is always that kid that's going to bomb the test. We used to go to Hilton Head when our kids were little, and you would hear these stories at Hilton Head about this massive alligator. I mean, huge. And you see alligators all over Hilton Head, walking across the street, on the golf courses, I mean, everywhere. And they had stories about this ancient, massive alligator. So if I took all the alligator's weights or lengths or however it is you want to measure an alligator, then 99.7% of all those observations, of all those lengths of alligators or all those weights of alligators, 99.7% of them would fall within 3 standard deviations of the mean of all my data. But I'm leaving room for this massive alligator that's out there. That's why it's not 100%. There's always potential for an exception to the rule. I did a problem one time about the weights of rats in New York City. And the professor said, you know, there are legends of the rats, of how big the rats are in the subway system in New York City. And they would say some of these rats, one of them has been said that it looks at least 10 pounds. Well, 10 pounds would be way outside 3 standard deviations of the mean of all the weights of all the rats in New York City. But he said you always have to leave room for that 10-pound rat. So that's why it's not 100%. You have to leave room for the exception to the rule. And that's why you don't say 100% because that's all inclusive and so definitive. So 99.7, that leaves 0.3 of a percentage point to leave room for that 10-pound rat or that 500-pound alligator. All right. So if I know that this is 68%, then doesn't it make sense that it's 34% one way and 34% the other way? I just cut it in half. Okay. If from here to here is 95%, then would it make sense that from here to here, let's see, what's half of 95%? 47.5. So from here to here would be 47.5%, and from here to here would be 47.5%. So my question is, from here to here is 13.5, because I've already got 34. So to get to 47, I just need another 13.5. So this little piece right here is 13.5%. These are not things I need you to memorize. These and this one down here, I need you to memorize those. But these down here, you don't have to memorize, but I want you to see how you can go figure them out. And then the last one is going to carry us to 99.7. Okay, so you can do it the way I did the other one, or you can think about this. Subtract the 2 there. Well, that would be 4.7%. Okay, so I'm 4.7%. I need another color. I'm 4.7% there and there total. So then I half it, and that's where the 2.35% comes from, because it's split between those two places. Now, if I were to add all of these up, I do not get 100%. I would get 99.7. Remember, you got to leave room for the 10-pound rat. So it does not all add up to 100%. 3 standard deviations away from the mean will get you 99.7. So the rule you need to memorize is 68, 95, 99.7. 68, 95, 99.7. Okay, the distribution of the ITBS vocabulary scores for 7th grade in 7th graders in Gary, Indiana is capital N, so I'm normal. The 6.84, that's my mu, and the 1.55, that's my sigma. What percent of the ITBS vocabulary scores are less than 3.74? Okay. Let's see, I don't like that little flare out. Okay. 6.84. And I need to get to 3.74. or less than a 3.74. So I need to be headed in this direction. So 6.84, I'm going to subtract one of my standard deviations. That's going to get me to 5.29. Subtract it again, and that's going to get me to 3.74. So here's my piece of data. And I want to know what percent, so area under the curve, is less than that. Now, less than that means goes all the way, like does not stop at 3 standard deviations below the mean. So we're including that, half a pound rat, because we're down here where things get small. So I can, let's see, if I do this, let's see, I can look at these numbers and I can see that I'm here. So I know from 2 standard deviations below to 3 standard deviations below, I'm 2.35. So 2.35, but that doesn't carry me all the way out. I need to get to 100%. Okay, so let me ask you this. Let's do this. The 99.7 leaves 0.3% left to get me to 100. Okay, so make sure you understand that. 99.7 will take me to 3 standard deviations, and that leaves me with 0.3% left to get me all the way to 100. Well, that 0.3% has got to be split between the 2 wings. So if I cut that in half, that's 0.15% on the far, far right and far, far left. So I'm talking about beyond 3 standard deviations. So if I know that I'm 2.35 here, and now I just need to know what's beyond the 3, that's the 0.15. So then if I add those 2 areas together, I get 2.5%. So the 2.35 gets me from 2 to 3 standard deviations, but remember, there is data out here. So I figured that out by taking, well, this is 99.7, that'll get me 3 standard deviations out. That leaves me with 0.3% left to get me to 100. I chopped that in half because it's in 2 wings. So I've got 0.15% left way out here beyond the 3 standard deviations below the mean. So I'm going to add those 2 pieces together, and that gives me my total area. Another way you could do that, because I want to give you multiple ways to attack this problem. Check out the 95%. So the 95% gets me 2 standard deviations out. Well, I want everything south of that or west of that. So if that's 95%, then I know that I have 5% left. Well, that's in 2 different wings. So if I chop that in half, that gives me 2.5% in each wing. That's below 2 standard deviations or above 2 standard deviations. So you get the same answer that way. Okay, if that's not sitting well, is that some good crunchy math? Pause it, rewind it, go watch that again, and make sure that sits okay. What percent of the scores are between a 5.29 and a 9.94? Okay, so 5.29 is here. That's 1 standard deviation below the mean. Here's my mean. And I want to go up to a 9.94. Okay, so if I add my standard deviation, that gives me 8.39. And if I add it again, I get 9.94. So that's 2 standard deviations out, and this is 1 standard deviation below. So I want this. I want to know what percent. So I want the area under the curve. oops, sorry, circled the wrong thing. I want the area under the curve that's between a 5.29 and a 9.94. So from here to here, I want all of this. Okay, well, I know one standard deviation out is 68%. So 68 plus. Then this little piece right there, I know is 13.5%. Add those together, and I get 81.5%. Again, make sure that makes sense. Okay? The distribution of heights of young women aged 18 to 24 is approximately normal, with a mean of 64.5 inches and a standard deviation of 2.5 inches. Sketch a normal density curve for the distribution and label. What percent of young women have heights greater than 67 inches? What percent of young women have heights between 62 and 72 inches? Okay, I want you to pause this, and I want you to see what you can do with this one without me holding your hand and walking you through it. If you get stuck, then hit play and let me get you unstuck, but then pause and keep going. See if you can get all the way through this one, and then hit play and check your answers. All right, so if I'm a normal distribution with a mean of 64.5, I have a standard deviation of 2.5. So if I go 1, 2, 3, this one, I'm going to write this smaller. Oh, no. 64.5, 67, 69.5, and 72. And this would be 62 and 59.5 and 57. Okay, so there he is. That's number one. What percent of young women have heights greater than 67? So that's all of this. And again, greater. So we're not stopping at 3 standard deviations. I'm not stopping at 72. I need to go all the way out. Remember, 3 standard deviations does not include 100% of your data. So if I were to add those pieces up, I'm going to get 16%. A couple different ways you can do this. I'm kind of more of a logic-y kind of girl. If I know that this middle chunk is 68%, then I know this is 34%. Well, I know this whole half is 50%, and I don't want the 34%. So I did 50 minus 34 and got the 16. You can't go in here and just add those two pieces together because you're missing that end piece. And remember, I just want you to memorize the 68, 95, 99, 7 rule. I don't want you to sit here and feel like you have to memorize every single compartment. If you'll know the 68, 95, 99, 7, you can piece together the rest. So there's number 2. Number 3, between 62 and 72. Okay, between 62 and 72. Okay, well, I know from here to here is 68. I know that from here to here is 16. So 84%. All right. Okay, so the standard normal distribution. So the standard normal distribution, which we already talked about in the last class, is a normal distribution. Its mean will always be 0. and the standard deviation is 1. This is your z-scores. All right, let's talk about why your mean is 0. If you are the standard normal distribution, then we are talking z-score. The z-score is the number of standard deviations above or below the mean. Well, if your z-score is the number of standard deviations above or below the mean, then what would this z-score be? He would be a 0 because he is not above or below the mean. He's dead on it. So your mean will always have a z-score of a 0. Then this is 1 standard deviation above the mean, 2 standard deviations above the mean, 2 standard deviations below the mean. Notice it goes to 3 on either side as well. So we talked about some chick 2 days ago where she had a stats test and a chem test, and we wanted to know how she did relative to her class. So we found her z-score, which told us how much above or below the class average she was. That's what this is. That was her z-score. So guys, let me tell you something. If you're doing your homework or a quiz or a test review or a test and you get a z-score that's a 12, something's off. Because look at this curve. This curve is centered around 0 and goes from -3 to 3. Now, could you have a z-score that's a little bit higher than a 3 or a little bit lower than a -3? Absolutely. Remember, it's only 99.7% of my data. But there's no way on God's green planet that you're going to have a z-score of a 12. It's just not going to happen if your data follows a normal distribution. You are not going to have a z-score of a -7. Your z-scores, honestly, guys, are going to live really within a 4 and a -4. But remember, 99.7% of the time, they're going to live between a 3 and a -3. 68% of the time, they're going to live between a 1 and a -1. 95% of the time, they're going to live between a 2 and a -2 because your z-score measures how far above or below in standard deviations your piece of data is. So, does the 68, 95, 99, 7 rule still apply? Absolutely. 68% of my data lives right here. 95% of my data lives right there. And 99.7 lives from 3 to -3. Okay, but what if we want to find a more specific area under the curve? The 68, 95, 99, 7 rule wouldn't help us, whether it was a normal distribution or a standard normal distribution. So think about, I forgot her name, but think about the girl's stats test score from a couple days ago. Her test score for stats, her z-score was like a 0.988. Like it wasn't exact. It wasn't exactly 1. It was just under 1. And her chem score was like a 1 point something or a 2 point something. I can't remember. So what if the z-score isn't exactly this nice round number and we want to find the percentage that's in between in some interval? So that's what we're going to work on for next time is all of these z-scores that are in between these numbers, all these decimals.